Welcome to the next lecture for Geotechnics 254. Jennings, a South African soil scientist in 1973, came up with a classification system, and he made the following statement. The systematic description of each layer of soil from the surface down to the bedrock provides the basis for the first assessment of the engineering properties of the soil. What he's basically saying is that if you have a soil profile and you describe it in the field, then you already have an idea of what to expect when you start construction on this particular site. So the lecture is on Craig 1.5, and it will cover soil description and the classification of soils. Soil description, you can either do it in situ, in other words in the field, or laboratory testing on disturbed soil samples. We also use undisturbed soil samples sometimes for certain of our tests. Then in the lab, we also do foundation indicator tests, which is basically the particle size distribution and the plastic properties, which is what we discussed in the previous lecture. The rapid assessment procedure is an in-situ determination of grading and plasticity based on appearance and feel of soil. In other words, you go out to the field, you describe the soil as you see it, what it looks like, what it feels like, and yes, even what it tastes like. For instance, if you take a bit of soil and you rub it on your finger and you rub your finger against your teeth, if it's not gritty, then you know you're dealing with a clay, and depending on that amount, you can actually determine even to some extent the percentage of clay. If you can feel it and it's gritty, then you're dealing with a sand or a silt. The clay or the silt particles determine whether the soil has cohesion and plasticity. Cohesion means the soil can be molded into a relatively firm mass at an appropriate water content. Plasticity, on the other hand, the soil can be deformed without cracking or crumbling. And there are various in-situ methods to determine the plasticity, and it's described on page 15 and 16 of the handbook. There are various soil description standards in the world. In Europe, they use the ISO 14688/1, and it's described, for instance, on page 17. In America, they use the ASTM D2487 standard, American Standard Testing Methods, and South African, we use the SANS codes, South African National Standard 633. It's in draft format at the moment, but it's used, and it's basically using the system as proposed by Jennings of MCCSSO. We heard about this in engineering geology already. It's an in-situ method where you look at the moisture content, the color of the soil, the consistency of the soil, what is the structure, the soil type, and origin. The soil type is whether it's a sandy, clay, or etc. Once you have taken the sample to the lab and you've done a sieve analysis, now you can get percentages, for instance, of the gravel and the clay and the sand, and the above description of 5% gravel, 35% clay, and 60% sand will be described as a clayey fine sand with scattered fine and medium rounded quartz. Whereas in the MCCSSO system, you don't have the percentages, so you can describe a soil, for instance, in this particular case, you would describe it as a clay sand with gravel. If you have those percentages, or so the clay is the secondary most constituent, then the 60% sand, it means it's the main constituent, so it's a clay sand and with gravel. In the soil classification systems, the soils are placed in groups based on their grading and plasticity, and it requires information about the grading and plasticity. There are two main classification systems used. First of all, the British classification system. And the difference between the British classification system and the American standard is the percentage of fines. In the British standard, the boundary between coarse and fine-grained soils is 35% fine particles, 35% particles consisting of silt and clay. If it's more than 35%, then it's a fine-grained soil. The British classification system looks at the liquid and plastic limits and is used to classify the fine-grained soils on the plasticity chart, which is given on page 20, and you can end up with descriptions such as SW, which would be a well-graded sand, or an MCCSSO, it's an organic sandy silt with high plasticity. And this is the plasticity chart. So depending on the plasticity index, the PI or IP, versus the liquid limit, your soil can then be classified on this chart and you have a good description. So CH, for instance, would be active clay, or a clay with a high percentage of active material, etc. On the other hand, the USCS, the Unified Soil Classification System, as used in America, the boundary between the coarse and fine-grained soils is a little bit higher, and it's 50% fine particles, 50% of soil, silt and clay. The Unified Plasticity Chart distinguishes between the clay and the silt, and again, the liquid and plastic limits are used to classify the fine-grained soils. In the USCS, we have these flow charts, the one for the coarse-grained soils and another one for fines. But for instance, here percentages play the major role. For instance, if you look at the gravel, if you have less than 5% fines, you have a CU of between greater or equal than 4, and a CZ between those ranges. You have a GW description. Depending on the percentage of sand, if it's less than 50% sand, you have a well-graded gravel. If it's more than 15% sand, now it's called a well-graded gravel with sand. And so you can go through all of these one by one, and at the end of the lecture I'll be doing an example of how to use this chart based on laboratory results. So if we look at this table, soil A, B, C and D. Soil A, we've seen before, actually we've seen this list, 100% of the particles is less than 20 millimeters and 1% is less than 0.02 millimeters. The liquid limit is 0 and the plastic limit is also 0. Soil B is non-plastic, that's what the NP stands for at the bottom. And then soil C has a liquid limit of 32 and a plastic limit of 26. If we then plot this on the semilogarithmic table, you will get the following curves, and based on the values of D10, D30 and D60, you can determine your CU and CZ. And that is what we're going to use to do classification. And I'm going to end the lecture here and make a separate video of the example. Thank you.